Hello, I am Brena, a senior academic mentor with ESM Prep.
And I am Andra, an academic mentor with ESM Prep.
And we're here today to talk about the ACT science section. The science section might be intimidating for some people who don't feel like they're really good at science. And it also might be really exciting for people who feel like they are very good at science. It's sort of its own entity. It's a particular type of reading test for the most part. And we're here today to talk about the outside content knowledge that you are expected to bring in when you take this test.
And I would say there, Brena, that the reason why this is so important is because most of the test is not actually based on outside knowledge, which should actually be good news. So if you find yourself wondering, should I take the ACT or the SAT? Because the ACT is the only one of the two that has a science section. I guess we both agree there that the science section is not really about science, apart from the things that we're gonna discuss about now. So have a look at this, and if by the end of it you're thinking, I could cope with that, then you're probably in a good position to take the ACT.
Exactly. So what do you need to know? This slide is purposefully a little bit colorful and vibrant and intimidating, but if you look closely at it, most of this information is probably information that you learned a long time ago. The order of the planets, there are mnemonics for that, the structure of an atom with the protons and neutrons in the middle and the electrons zipping around. That's something that you've probably been introduced to in middle school, maybe even elementary school. So it's not AP level knowledge.
Definitely not. And Brena, just looking at that slide for a second there, what would be one of the best ways to go about is, I'm just thinking, obviously we have resources at ESM to go through these things, right? And we definitely don't expect you guys by the end of this presentation to go away with all the slides learned, okay? So there will be resources that we can share with you at the end. Don't feel like you need to write all this down. This is just to give you an overview of what's available.
Yes, definitely. So what does an ACT question look like that requires a little bit of outside knowledge in order to answer? It probably will look like you're pulling some information from the passage and some information as outside content knowledge. Here's an example of a question where the answer choices are 2x2s or 50-50s. Half of the answer choices say yes, half of them say no, and then the explanations look very similar to each other. So what's different? I see that word is different. So what is the question? Suppose that air temperature in the playa varies between 4 degrees Celsius and 47 degrees Celsius. Can ice form in that temperature range? The answer is maybe if you're very used to Fahrenheit, this is a hard question. If you're used to Celsius, this is probably not a terribly hard question. Most science is conducted in Celsius or Kelvin, but on the test, Celsius. So what do you need to know? freezing point of water is 0 Celsius. Boiling point of water is 100 Celsius. So can ice form between 4 degrees Celsius and 47 degrees Celsius?
No, it can't.
No, it can't. All right, half our choices are gone. Haha.
That's great.
And then the second part of this question, would this information support the explanation of scientist 2? This is a passage type that has dueling perspectives, and I copied over the blurb at the beginning, and I copied over perspective number 2. So scientist number 2, because that's all you need, and you don't even need to read this to answer this question. I included it because it defines playa, and that's kind of nice, knowing what you're talking about. Scientist 2 says snowmelt from surrounding mountains does collect in the playa during the spring. However, the temperature in the playa does not get cold enough for ice to form. That is what Scientist 2 claims. So if the temperature is only in a range where ice cannot form, then that supports Scientist 2's explanation.
That's a great way to go about it. And I just want to highlight some of the very key things for a question like this, right? First of all, how do we recognize it? The 50-50 is really, really important. Then the fact that just by identifying one word in each answer choice, you can already get rid of 2 of them very quickly. And finally, understanding that sometimes these questions are a combination of information in the text and outside knowledge. But it doesn't always happen. Sometimes it's just outside knowledge. And obviously, most of the time, it's just information in the text.
Yes. Outside content knowledge questions can also ask you to explain why something happens. So which of the following statements best explains why the reaction described in fact 3, so I copied fact 3, requires a high temperature and pressure? The answer choices, again, are kind of split into pairs. We have the ones that talk about protons and the ones that talk about electrons. Are protons positively charged?
Yes, they are. Protons are positive.
Are electrons negatively charged?
Yes, because electrocuting yourself is a negative thing.
Okay, so darn, we don't get to eliminate anything based off of the info before the comma. Now I'm going to compare the info after the comma. Do like charges attract each other, or do like charges repel each other?
And again, some of you might not be familiar with what like charges mean. What they mean is 2 things that are either both positively charged or both negatively charged, okay? And when you have 2 charges of the same type, they actually repel each other. And if they are opposite charge, they attract each other, which is why we say that opposites attract. That genuinely comes from this chemistry fact, okay?
So we are able to eliminate the 2 answer choices that claim that like charges attract each other. Now we look at fact 3. A pre-MS star becomes an MS star when the star produces the majority of its energy by fusing hydrogen nuclei. Parenthetical info for the win at its center to make helium nuclei. So does fact 3 give a hoot about electrons?
Doesn't look like it.
It only cares about protons.
Mm-hmm.
We got it.
And Brena, you also pointed something very interesting there, the fact that it's in a bracket. And on the previous slide, we also saw that there was some information in the text itself that was in italics. Do you want to just make a comment on that? Because I know it's something we're going to see again and again in the questions.
Yeah, if you're ever doing a word search, trying to find information in the text, definitely look for funky punctuation like that. Look for italicized things, look for information in parentheses, because that's often where they will tuck in a definition that you might need. And let's take a look at this next question. Which of the following best explains why equal masses of oxygen and carbon dioxide at the same temperature and in the same sized vessel have different pressures? The pressure exerted by O2 was less because there are fewer O2 molecules per gram than there are carbon dioxide molecules per gram. Less because there are more. Okay, so we've got fewer and we've got more. We've got fewer and we've got more. And we have less or greater. Looking at the graph that relates the mass of gas added versus the pressure, for any given mass of gas added, the pressure of oxygen was greater than the pressure for carbon dioxide. So that much we can narrow it down. The pressure exerted by oxygen was greater. Now, why?
But there are different ways to look at this one, right? I guess there are two scientific facts that might help here. We either know that there's a connection between pressure and the number of particles, or we know how to compare number of particles in a certain substance. Okay, so we can discuss about the first one first. If the pressure is higher, does that mean that there are more or less particles there? And the easier way to think about this is that pressure, when we're talking about pressure in environment, it's the pressure against the walls of that container. Yeah. So think about it. If you have a certain number of particles and they're pressing against the walls of a container, will they press more if there are more particles?
Yeah.
Yeah.
If their average kinetic energy is the same, which it is.
Exactly. Yes. And sometimes things like, seeing the same temperature in the question, we might not even need to understand why those are there, these other little facts that they tell us just to make sure that they're telling us the questions fully. But in this case, just understanding that there's a direct relationship between the number of particles and the pressure in a certain container, that should be enough to answer the question. Another way to go about it is to think, thank you. Another way to go about it is to think, okay, if I have a gram of oxygen or a gram of CO2, which one of them is going to have more particles in it? And this might be something that's a little bit difficult to visualize for this question, but more generally speaking, for the purpose of this test, it's really useful to know how to equate numbers of particles with the amount of substance. So we actually put here for you an equation that you really, yep, there you go. We're both doing the same thing. This equation, really, really useful. And if you do decide to take the ACT, and if you are working with a mentor, they can definitely walk you through this one. It just takes a couple of minutes. And once you know it, it will be a lifesaver for many types of problems.
And it will also help in chemistry class.
Oh, yes, for sure. I would like to say also in life, but I'm not sure about that one. It's not one of those.
Tire pressure?
Maybe.
Sometimes you also want to pull in just a little bit of outside content knowledge to comprehend an unfamiliar setup. So this is more visual thinking than, strictly speaking, outside content knowledge. This is making sense of, what do gases do? What do liquids do if you pump them through a tube between two vessels? So this question, suppose that the trial in experiment 1, so this is experiment 1, with 0.25 grams of zinc is repeated, okay? Except that the inverted graduated cylinder is replaced by inverted test tubes, each completely filled with 60 milliliters of water. Okay, so I actually didn't put the graph that we need from experiment 1. So we can't fully answer this question, but we can make sense of the figure.
I think it might be on a different slide, but the most important thing is to make sense of the figure.
Yes. So this figure, the question talks about the inverted graduated cylinder, and you marked the inverted graduated cylinder. What the heck is it doing, and how does it relate to water and or gas? Like, what is happening here? 2 experiments were conducted to study the production of hydrogen gas in this reaction. The apparatus shown in the diagram below was used to collect the gas that was produced in each trial. And then if the diagram doesn't make a whole lot of sense, look below the diagram. As gas was produced in the stoppered flask, it exited the flask through the outlet tube. In the outlet tube and displaced the water that had been trapped in the inverted graduated cylinder. So there was water here. Gas came in and allowed some of that water to leak out of the tube, or out of the cylinder and into the vessel. So it displaced with gas. And then that allows you to measure the gas that was displaced. So the volume of water displaced equaled the volume of gas collected.
Now, Brena, you did bring up a few super important things here. One of them is that it can be useful to read about the experimental setup in the actual text, right? And if you have already started ACT prep, you probably know the thing that we say all the time, which is do not read the text first, try to read as little as possible. But if you have an experimental setup where your outside knowledge is not really helping you, trying to read as much as possible about the experimental setup can be quite useful. For those of you that have done science in school and are used to conducting experiments in biology and chemistry, it's definitely going to come in handy to understand the system just by looking at it, just from the picture. Sometimes you're not going to understand it fully even after you read the text, but as long as you get some sort of feel for what's happening, that should be enough to answer the question. So if it looks like something you've never seen before, which is likely that you will see, just don't panic and just try to make sense of it with what you already know.
And basically do a word search. Like I saw the inverted graduated cylinder was replaced by inverted test tubes. Okay, so what role does the inverted graduated cylinder play? I found it in the diagram, I found it in the text, and I found an explanation. The volume of water displaced from the inverted graduated cylinder equaled the volume of gas collected. And with the graph that is figure 1, you would be able to answer the question. and a little bit of math skills too.
Not that much math, definitely not as much math as in the math test. But would you say it's fair to say, Brena, that if you're okay with the math section, the math in science should not worry you?
Yes, I agree entirely. You're not allowed to use a calculator on the science section typically, so you can expect that the math is fairly straightforward. It's going to be estimating, it's going to be doubling something, maybe multiplying by 10, which is just adding a 0 or scooting a decimal point. It's not going to be anything involving pi or e. So it's going to be fairly doable math. With that said, you definitely want to pay attention to units. Units are very important when your numbers mean something on the page. This is study 4. So in study 4, the researchers trapped birds for 10,000 hours per year. Thus, how many insectivores were trapped in year 2? Okay, well, let's see. This is the year. This is year 2. Where's insectivores? Insectivores are the diamondy ones. Okay, so that's 80. So is my work done? Is it 80? Because that's an answer choice.
Better read that question.
Dang it. Okay, maybe I didn't read what the 80 is measuring. What 80 what's? 80 captures per 1,000 hours. Okay, so if I trap for 10,000 hours in year 2, and I have 80 captures, 80 captured insectivores per 1,000 hours of working. The 10,000 and the 1,000 reduce, and I'm making these 80 captures 10 times over. I'm actually making a total of 800 captures.
So that's a nice way to do a proportion problem there very easily. And proportions are definitely one of the few math skills that you need in this part of the test. Percentages, again, very important. And conversions, multiplication, division by 10 or powers of 10. But I would say that's pretty much where it ends, right, Brena?
Yeah,
you're probably not going to see logarithmic scales that you need to do calculations with. That's too advanced for this. You're not going to need to do very, very early calculator operations. So hopefully the math side of it, not too off-putting.
This one looks so mathy.
And this is actually one of my favorite questions here, because it's actually not an outside knowledge question, but it's made to look like an outside knowledge question, one that can definitely be panic-inducing. Tell us more about it, Brena.
The question asks, if the mass of the sun is 2.0 times 10 to the 30th kilograms, oh goodness, what is the mass of Algol or Algol C?
Oof.
Luckily, you don't have to pronounce things correctly to get it. All right, so maybe you're reading this and you're thinking, what the heck does the mass of the sun have to do with the mass of this other thing? And if you look at the text of the test, there is an italicized phrase, and there is a parenthetical. I like the parenthetical. Ooh, and I even see algal C, algal C. All right. So it looks like algal C is 1.7 solar masses, and one solar mass is equal to the mass of the sun. And my question tells me that the mass of the sun is 2.0 times 10 to the 30th kilograms. So mass of algal C is 1.7 solar masses, where one solar mass is 2.0 times 10 to the 30th kilograms.
And
Okay.
that's as ugly as the math you need to do gets. Just need to know how to multiply 1.7 by 2.
Whew. So you are expected to know some basic math, how to double something, how to scoot a decimal point.
Mhm.
You are expected to know the states of matter. So boiling point is between liquid and gas. That's also the same temperature as condensing, going from gas to liquid. And melting and freezing are melting from solid to liquid, freezing from liquid to gas, or liquid to solid, but the same temperatures. So you have these important temperatures for different substances, and the different states of matter behave differently. So a gas is going to expand to its container. A liquid is going to conform to the shape of the container, but not change volume.
Mhm.
And a solid is solid. The word temperature is interchangeable with the average kinetic energy of the particles. Know the Celsius scale, specifically as it pertains to water. Know the parts of an atom. So we mentioned that before. Know the parts of a chemical reaction. So what the coefficients mean, what the subscripts mean, which side is the reactants side and which side is the product side. How experiments are set up. So how you make a control group to compare against. And opposites attract. So these are all things that are general knowledge that you will be expected to know on pretty much every science test.
And then there's the other side of things, which, as you might notice, is mostly biology. And that's what you might need to know. And I will say with the ACT, they are always likely to throw something out there that hasn't been on the test before, something that's very random. But there's a lot that you can do just by following the logic and eliminating at least two answer choices and then guessing. So this is why we're putting this knowledge under you might need to know. If you already happen to know some biology, if you've done it reasonably recently, then it's definitely worth recapping these facts before a test. But otherwise, it can be way too much to learn just for the sake of maybe getting a question. Okay, so especially photosynthesis is something that comes up a lot. And even if there isn't any outside question about it, it's something that is useful to understand, at least a little bit, because it's just going to make the whole text a little bit more comprehensible. Also, just knowing a few things about DNA. What is DNA? What is it used for? Where do you find it? That again tends to be a favorite topic. In theory, you should know a thing or two about the different types or I guess categories for a species and the higher level taxonomy for a species. But again, very, very niche knowledge, which has only appeared on a couple of occasions. Same with the order of the planets. So If you happen to know it, that's great. You're putting yourself in a very good position. Otherwise, don't worry about it too much. One thing that has, however, come up a lot, and to be fair, which is useful to know anyway, is the pH scale. Okay, so knowing that something is acidic if it has a pH below 7, that it's basic if it has a pH above 7. We see this question come up again and again in different formats, and it can really, really help you understand a text better. And the others, again, just very niche little facts. And we have a full fact sheet document, which if you are working with one of our mentors, you've probably received. And we definitely recommend you look into that, especially as the test comes closer. It's just good to revise some of these things in advance. So I think what we're gonna do now, Brena, is we're gonna discuss about a few more general bits of outside knowledge, and then we're just gonna go through a couple of topic-specific examples. Okay. So what we wanted to discuss are a few general terms about designing an experiment. Obviously, each one of the science texts deals with some kind of experiment. There will always be some kind of data, or at least some claims and conclusions from data. But not all of you have had the chance to actually conduct experiments in school. And even if you have, perhaps you are not very used to some of these words. So we just wanted to discuss them a little bit. Well, one of the main things is a control group. And you will find that most experiments have what we call a control group. This is one part of the experiment where we do not change the state of what we're trying to test. We're just doing the boring experiment, which is what would happen if we didn't change anything in this context. Basically, what is the most boring state, right? So, for example, if you want to see what happens if you feed a kid a lot of chocolate, the control group is you don't feed the kid a lot of chocolate, and then you just observe and see what happens, and that's your control group. So it's the most boring situation. Okay.
It's sort of like a y-intercept. It's an initial.
Yeah, I like that. Yeah, if you are in the mathematical mindset, it is basically the y-intercept. I love that. That's a nice way to put it. And then there's a positive control, which you don't need to remember under this name, but what we might see sometimes are questions about why the scientist decided to do a certain thing. So we'll try to explain a positive control in that context. So this is a group on the test that is expected to give a certain result, okay? So for example, you want to see if you put your TV in water, is it going to work, right? Well, first of all, you need to know whether your TV works in the first place, right? And so what you need to do is you need to actually test your TV outside of water first. That's a positive control. It's basically a way to make sure that your experimental setup works as it should before you go and you do modifications to it. Okay. So very often, if you have a question where they change the setup, for example, the diagrams that Brena was talking about, if it looks like they're just testing the setup by itself, that's a positive control. They're just doing it to see if the setup works properly.
Cool. And if it comes up, metric conversions, it is fair game for a metric conversion question to show up using these prefixes. You're not going to see the you're really not going to see weirder ones unless they define them for you. But centi is fair game, milli and kilo are definitely fair game, maybe micro.
They're
Yeah.
definitely useful in maths as well, so they're worth learning.
Yes. And knowing what you're looking at when you see a unit. So if something is measured in liters, it is a fluid volume, a liquid volume. If something is measured in grams, you are measuring the mass. If you're looking at the density, then you can expect grams per liter, maybe. So you can see units and know what you are measuring, and that's helpful. Now let's try it. This question, based on figure 1, here is figure 1, the results of experiment 1, okay, I guess all the results of experiment 1 are in figure 1, are best modeled by which of the following equations? Okay, well, it looks like it's a straight line. It looks like the independent variable, the variable that we are changing, is the block mass. And we are measuring the effect on the pulling force. So we just want the equation. We don't want like the rate of change of the equation. We're not measuring the speed at all in this question. So purely looking at the axis labels, I'm not sure why block speed is even an answer choice. From there, what makes sense? Helpful outside content knowledge. When writing a mathematical model, the goal is typically to express the dependent variable as a function of the independent variable and focus on the units. So we got rid of 2 things. Now we have to do a little bit of math, just a little bit. Let's pick a point that is really clearly marked and easy to work with. 1,5 is clearly marked and easy to work with. You could also use 0, 0, but that works for both answer choices. So I'm going to use 1,5. If this weren't such a perfect line, I would be cautious and I would use the farthest reference point that I can, just so that I'm spreading out my reference points. But I'm going to use 1,5 because it's a very perfect line. If I plug in 1 for my block mass, which answer choice gives me 5? Yay. And so I don't even need to know what newtons are because they're not expecting me to. They're just expecting me to connect the dots, quite literally. Try. Oh. Now the next few questions have a little something to do with experimental design and or units, and a little something to do with chemistry. And so that is why I am resharing the pretty pictures about chemistry. All right, 2 questions. 26, a student claims that if the masses of 1 cubic centimeter of any solid and 1 cubic centimeter of any liquid are compared, the mass of the solid will be greater. Do the data in table 1 support this claim? Okay, so here's table 1. And what is the claim again? The masses of 1 cubic centimeter of any solid and 1 cubic centimeter of any liquid are compared. The solid would have a greater mass. Okay, so here are the solids, here are the liquids. Do we see? Ooh, the answer choices mention lead and mercury specifically. So let's look at lead and let's look at mercury. Now, what did the answer choices say?
Well, I see that there are a few words that are different. There's obviously the no and the yes.
Cool.
Then obviously we only have those two. So first of all, we need to understand which one has the higher density. Okay, and thankfully they're nice in the table. They actually tell us where they're measuring density. So all we need is to check the density and we see which one is denser. And that seems to be mercury. So what do we do with that knowledge? We know that mercury is denser. There you go. That's out of the window. What do we do now?
So mercury is under the liquids, and it's a liquid with a higher density than any of the solids listed. So J is a true statement. G is also a true statement, but the student was claiming that any of the solids would be
more dense than any of the liquids.
Yes. Actually, what it's claiming is the mass. If the mass of 1 cubic centimeter. So we do sort of have to understand the connection between density and volume and mass.
Yep. How are we going to do that?
Well, we could look at the units. So if you have 1 cubic centimeter of something that has density, let's see, we only care about mercury, 13.59 grams per 1 cubic centimeter. Notice that the cubic centimeters cancel, and the number that we had under density was the mass of that sample, of 1 cubic centimeter of that sample, of that substance. So yes, the units are different, but the numbers that are measuring density are actually measuring the mass of 1 cubic centimeter also. So we get to compare those.
What I was going to say is this is such a good trick if you see a quantity that you don't know much about, right? If you don't know what we're measuring this quantity in, if you don't know how to link density, mass, and volume, for example, you don't need to remember the formula from school. You can just follow the units. It's generally one of the simplest and most effective bits of advice I could give.
Cool. And the student was wrong.
Students tend to be wrong. Do not take that as official advice. But on these tests, when a student makes a claim, very often that claim is wrong. There are specific texts where students make claims. They tend to be wrong, but it's your job to prove that. And in doing so, be right.
Now let's look at question 29. According to figure 1, so this one's a graph. I'm sorry, 100 grams of water at 4 degrees Celsius would exactly fill a container having which of the following volumes? Okay, so each answer choice just has a different number of zeros. And each answer choice is in cubic centimeters. So according to the figure, 4 degrees Celsius, that looks like it's at the peak. It looks like it has a density of 1. So that's 1 gram per cubic centimeter. That's our density. And if we have 100 grams, oh, so I'm going to start with this number because it doesn't feel like a rate to me. It just has one unit. So I'm going to write that down, 100 grams. And then I'm going to use this, but I'm going to flip it upside down so that grams cancel and I learn something about my volume. So this is a 1-to-1. Grams would cancel. I would be left with cubic centimeters. Specifically, I would be left with 100 of them.
Again, simple example, just following the units.
Yep. And I like these questions because I'm calling them intimidation questions. They have italicized stuff and even parentheses in the question. And so that might lead you to think that you're expected to know something. You're expected to have some outside content knowledge. But knowing 1 millimole of carbon dioxide has mass of 0.044 grams, goodness. How many trials resulted in the production of at least 1 millimole of carbon dioxide? This feels like I'm going to have to do some crazy conversion, but I'm not. This is giving me mass of carbon dioxide in grams.
Mm-hmm.
And I'm told that 1 millimole has this mass, and I'm asked how many have at least that many millimoles. Okay, so what I'm really saying is at least this mass. So I'm just seeing how many of them are bigger than or equal to that number. And it looks like it's all of them.
It's all of them, yeah. That was easy.
Cool. Winning. I didn't have to do any math at all.
Mm-hmm.
And then 14, assume that room temperature is 25 degrees Celsius. Oh no, I'm gonna have to do something with freezing. Oh, I don't know. In how many trials was the Diet Cola tested at a temperature lower than 25 degrees Celsius? So here you do a quick visual scan for degrees Celsius, anything that mentions degrees Celsius. So table 2, this entire column mentions degrees Celsius, and we want lower than room temperature. So we want lower than, strictly lower than, not equal to.
Mm-hmm.
So 25 is out, 45 and 60 are out. And then we look at this other table. Table 1 doesn't mention degrees Celsius. So how do we know what temperature it was at? Well, then we extend our word search into the text, and we see that all 4 of these trials were done at lower than room temperature. So it was these 4 trials plus trial 5. So a total of 5 trials were done lower than room temperature. No math, just bigger than, less than word search.
And this is just to show you once again that if there's one bit of outside knowledge that you need to know, is that the freezing/melting point of water is at 0 degrees Celsius. We're not even going to go over it because it's the same idea, and there's so many others. It's such an important bit of information.
And just to drive that home a little bit more, this entire passage is about mass, volume, density, melting point, and boiling point. So this entire passage, how many questions is that? 1, 2, 3, 4, 5, 6, 7. 7 questions over that concept. And then you happen to have a table with some specific samples listed off, but you're just testing comprehension of those concepts. Specifically, if we look at question 13, it says, suppose that the temperature of sample D is increased to 890 degrees Celsius at 1 atmosphere of pressure. Will the sample's density be lower than or higher than it was at 20 degrees Celsius, same pressure? So they're keeping the pressure constant. That's just noise to say that that is something that isn't changing. So that's something that isn't changing.
Yep.
So let's see, the sample's density lower than or higher than at 20 degrees Celsius. Well, if you're increasing the average kinetic energy and you're not increasing the pressure, if you're increasing the temperature, it's going to expand. Even if it doesn't change phases, it's going to expand.
Yeah, so this is looking at the connection between pressure and temperature and volume. And there are different ways in which you can apply this to questions, but understanding this connection and how changing one of these parameters changes the others is, again, really, really useful. And I think this is one of those things that can be useful in life as well.
Yes, I agree. The final piece of this puzzle to answer this question is to ask yourself what the heck is up with 890 degrees Celsius. Like, that's a very specific number. Why are we interested in that number? And we are interested in that number because it is higher than the boiling point. So if it's higher than the boiling point for sample D, then at that temperature, sample D will be a gas. So yes, gas. And the density will be lower because the particles are more spread out. Cool. When a solid metal M, such as iron, nickel, or zinc, is placed in an aqueous hydrochloric acid solution, a reaction that produces a gas occurs. Consider the balanced chemical equation in the passage. So I've provided the balanced chemical equation. Based on that equation, if 10 moles of hydrochloric acid are consumed, how many moles of hydrogen gas are produced?
Now, this question uses some really, really specific chemistry knowledge. If you don't know the knowledge, you might really not know how to go about this. But if you want to learn it very quickly, the takeaway is that the numbers that we put in front of a substance in a chemical equation actually refer to the proportion of the moles. Okay, so what do we do here where there isn't a number? There you go. We can just assume that that is 1. Okay, so what that means is that for every 1 mole of the metal that we use, we're gonna find 2 moles of the acid in there. Okay, we're gonna have 1 mole of the salt and 1 mole of the hydrogen. So what they tell us here is that in the case of this reaction, we're going to have 10 moles. Brena is going to show us what we can do with that.
All right. So you can think of this like an equation. 2 moles of hydrochloric acid used up equals 1 mole of hydrogen produced. And anytime you have numbers with units equal to each other, you can use those in a conversion. And so if you have 10 moles of hydrochloric acid that we're using up, every 2 moles of hydrochloric acid that we use up produces 1 mole of hydrogen gas. And that would cancel the moles of hydrochloric acid and leave you with the moles of hydrogen gas produced, specifically 5.
Again, proportions, back to the outside knowledge for maths, it's proportions more than anything else. They're very, very useful. And because we only have a few more minutes left, we're just going to take you a little bit through a couple of biological examples as well, where, as I was mentioning before, it's not that much about knowing the information, it's about having seen it before, just so you don't feel completely lost, okay? In this case, we're looking into some really, really ugly maps. And the passage on the left in particular, if you've never seen genetics before, if you don't know what a gene is, if you don't understand that a gene is a bit of DNA, that it has different regions on it, then information like this can be really, really off-putting and might make you wonder what is happening here. But there are a few key points to note. First of all, there's an actual key. Sorry, Brena, if you want to just go back. First of all, there's an actual key here that will try to help you make sense of it. And the other one is, if you know some basic biological concepts in advance, they will definitely speed up your understanding of this. On the other side, we are looking into meiosis, which is a process that you've definitely heard about if you've done biology before. But even if you don't know anything about this, just really give yourself the time to look at the image, and that will be enough to help you understand. In particular, the places where you see that these weird ugly sticks are changing number, there you go. What is happening there? And then they're changing number again. Even if you think, oh, I did meiosis at some point. I remember it was impossible and I never learned anything from it and I hated it and there's no way I'm going to be able to do this text. I'm not even going to try. Don't go there. Don't do that. Because if you really use the image, you should be able to understand at least most of the questions, if not all of them. Okay. And finally, there's something to be said on the next slide about a very popular type of question that has to do with energy and ATP. This is a strict outside knowledge question at its purest form. And you do need to know basically, especially about ATP, DNA, and amino acids. These are things that are useful to know. Yep, there you go. We don't need that at all. It's not going to be helpful. And what's interesting about this question is it can definitely trick you into looking at the text. Okay, you might find a lot of time just looking at the text. So if you don't realize immediately it's an outside knowledge question, a couple of things to know there. The text reflects reality. Yeah. So unless there's a claim from a student or a scientist, the text will reflect reality. Any question that asks you about the interpretation of real data, or any text that asks you about what happens in reality, reflects what you would expect in real life. So if you're not sure where to look in the text, even if maybe the answer is there, just take a step back and ask yourself, okay, but can I just figure this one out by myself? Is this something that I could just use my common sense to answer? And in this case, that's definitely the only way to do it. Yeah, and then we have a few other examples here, right? Again, other things, photosynthesis, which again comes back to energy, keywords, ugly keywords that help you understand a bit more about the text at hand. But the best thing you can do for these is to just have a very, very high level recap of what the question is about. Then looking at photosynthesis very briefly in the outside knowledge sheet that we have. And then if you go to the next question, Brena, again, we'll see that they're talking about the same topics in bio. Yeah, there you go. So again, we're talking about DNA. Again, we're talking about amino acids and about proteins. So the content does tend to be a little bit repetitive, but it's also a little bit more qualitative. It's not that much quantitative. In biology, it's not really about learning an equation or following the units. It's just being familiar with some high-level topics, which can help us navigate the content. Okay. I think we can even skip this one because it's probably the same takeaway. And finally, we go to physics, which is probably the most off-putting of all of the topics, just because there's so much advanced physics, and it's likely that even if you've done physics in school, you haven't seen all of the physics that they ask you about. But the questions that are outside knowledge are most likely things that you're likely to know about. For example, this one is about global warming, climate change. And it's a very hidden bit of outside knowledge. It's quite a hard one to do, but they are expecting you guys to understand that if you have visible light that's being reflected, will that cool or will that warm the atmosphere, the surface of the earth, right? So here you can bring your own knowledge about the effects of certain gases on the climate, the fact that when you have more heat being trapped, it will get warmer. And yeah, this goes back to greenhouse gases, which if you know about, makes this very, very easy. And if you don't, makes this a very, very difficult question. And then, yes, there are a few other bits of knowledge from physics. They definitely like acceleration rates. They definitely like forces. They like gravity. In this case, acceleration, if you've never heard of it, or if you haven't done it in a while, you might be wondering, okay, what is the formula for that? Again, it's just a case of follow the unit, okay? Physics is full of formulas. It's probably one of the most formula rich of all sciences when it comes to outside knowledge. But if you just follow the units, it will help you really understand how to measure things. And I think that's us. Yeah, so what we've done here is we have put together some resources. Remember that we do have the outside knowledge sheet. So if you haven't seen that already, please do reach out to us. We have our emails here. And just try to do as many questions as possible. One of the hardest things about outside knowledge questions is actually spotting them. So try to do that as much as possible. And don't worry if come test day, there's a question and you realize this is outside knowledge. I can't believe it. I just can't do this. Chances are
there will narrow it down.
Yes, narrow it down.
Probably get rid of something from some of the answer choices that you know can't be it.
Yeah.
And then that increases your probability of guessing the right answer without doing it.
That's exactly it. Yeah. So you have at least a 50-50 chance of getting it. And they're the one type of question which, frankly, we're okay with you missing. You didn't hear that here. But, you know, sometimes it can happen. You definitely don't want to to me is too many, but this is one of those that might happen. The best thing to do is to just be prepared and start early on, because you don't want to cram up many facts right before test. That was it. Thank you very much, everybody, for listening to us, and we will send this to everybody later as well. So do feel free to ping us at any point for anything.
And the slideshow does include a few extra questions, a few extra examples at the end after this slide. So if you want a copy of that, just let us know.
Absolutely. Yeah, it's good practice. Thank you.